All right, this is lesson 9.5, and what we're going to do today is start looking at some sequences that start to alternate and ask ourselves what happens if we throw an alternator on them. So this series, which is just adding up 1/2 over and over and over again, obviously gets bigger and bigger and bigger, and it diverges, it heads off to infinity. But if we start an alternator on this and go 1/2 minus 1/2 plus 1/2 minus 1/2 plus 1/2 minus 1/2, it might appear at first that this converges to 0, but the problem is that every other partial sum is flipping back up to 1/2. So for example, if you added these 3 terms together, you would get 1/2. But if we added 4 terms, we would get 0. If we add 5 terms, 1/2, 0. So this series will diverge as well, not because it goes to infinity, but because it oscillates between 1/2 and 0. It can't settle down on just one sum. Right? So that's what's going on there. This series here, 1, 4, 1/4, 1/9, 1/16, that's 1 over n squared, which we know converges. It's a p series, and the p-value is 2, which is which is greater than 1, and therefore that's why we know that that converges. Okay, so if I add up all these terms and that stays contained, that equals some value, what happens if I subtract every other one? Well, certainly that's going to give me a smaller amount. If I'm taking away every other value instead of adding it on, this is going to be smaller than this, right? This sum would be bigger than this. So this is smaller than a converging series. So this must converge as well, right? That's just using a little logic. We'll be a little more official in a second, but that's what we know about that, okay? But now we get this series, and this is the harmonic series, which we know diverges. P series with a p-value of 1, we know that this is going to blow up. But if we subtract every other term, is that enough? We know that this series is bigger than this one, but just because I'm smaller than a divergent series doesn't mean that I have to converge. I might diverge there. So this is still a little bit of a mystery, right? And the same thing here. If this is 1 over square root of n, which we know diverges, if I did every other term, well, that's going to make it smaller, but again, I'm going to have a little bit of a mystery. So let's take away the mystery. We're going to now talk about what happens when you put an alternator onto a series. So if we have a sequence and we put an alternator, it doesn't matter if it's -1 to the n or -1 to the n plus 1. That part doesn't matter. It doesn't matter if you start positive or start negative. If you're alternating back and forth, that series will converge as long as your sequence is heading to 0. So our sequence has to be heading to 0, and it has to be a decreasing series. In other words, you can't have a sequence doing this, like heading to 0 but getting bigger and smaller and bigger and smaller. Some sequences will do that. If that's happening, this doesn't really apply. But as long as it's just a sequence that's heading off to 0 like that, and it's constantly decreasing, and you throw an alternator on it, you're guaranteed that the series will converge. Okay? Doesn't matter if it diverged before or not. So we already said that this series converged and we're less than this series, so therefore this has to converge as well, right? Like we didn't need an alternator to help us. We'll talk more about that in a little bit. But what this new idea helps us to say is this series diverges, but now we slap an alternator on it. We now have -1 to the n plus 1, times 1 over n. So the sequence, 1 over n goes to 0 and is decreasing. Now we put an alternator on it, this series converges. By subtracting every other term, that's enough to bring that sum away from growing and growing and growing and into a place where it stays contained. Right? Same thing here. This series diverges, but now I'm going to put an alternator on it. So the sequence 1 over square root of n goes to 0 and is decreasing. That's all I need. If I have a sequence that goes to 0 and is decreasing and I put an alternator on it, that series will converge now. That alternator has enough power to make that happen. Okay? So let's apply it to a few other ones. So if I have this series here, there's an alternator. Okay, so right away I'm going to ask myself, does that sequence go to 0? Check. Does that sequence decrease? Check. All right. Both of those things are true. So with an alternator, this series converges. Here I'm looking at an alternator onto this. So I ask myself, does this go to 0? Absolutely. Does it decrease? Absolutely. Both check out. I have an alternator on it. The series is going to converge. Okay, so we're talking about specifically if we see an alternator on it. This one here, that sequence 1 over n to the 10th plus n to the 4th plus 5 is going to 0, and it's decreasing. Check. All right, so our series converges. If I look at this one, I have an alternator, but I'm looking at my sequence, 4n over 5n minus 3. Does that go to 0? No. So the alternating series test doesn't work here. In fact, because the sequence is not going to 0, this series diverges by nth term test. All right, so you do have to look and say, what does my sequence do? Right? So right here, my 4n plus 1 over 5n plus 3, that's a geometrical type. That's going to get smaller and smaller and smaller and smaller. So yes, that's heading to 0. Yes, it's decreasing. So this series converges. Okay. So now we're going to talk about the two kinds of convergence, because you kind of already seen, like some of these series didn't need any help and some of them did, right? So there's two kinds of convergence that happen out of this, an absolute and a conditional. An absolute convergence means the series would have converged without an alternator. Okay? You didn't need the alternator on it to make that converge. Okay? Conditional convergence says the series would have diverged without an alternator. Okay. So basically what we're going to do is, if we're asked to say which one this is, we'll take the alternator off and ask ourselves, does that still converge or does now that diverge? Right? So for our original, this one here, which is negative 1 to the n plus 1 over n squared, for sure that converges because there's an alternator on a sequence that goes to 0 and gets smaller. But what if we pull the alternator off? What if we just had 1 over n squared? Well, that still converges, right? It's a p series, it converges. So it doesn't need the alternator. It's fine that it's there, but it didn't need it to make it converge. So we say that this is absolutely convergent. Absolutely converges, or converges absolutely, or however that. The absolute means we did not need help. We didn't need the alternator. But if we look at this one, which again is negative 1 to the n plus 1, 1 over n, yes, that converges because it's an alternating series with a sequence that's heading to 0 and decreasing. So we know it converges. However, if we take the alternator off, that series diverges. So the only reason this is converging is because of the alternator. Therefore, this is conditionally convergent, or conditionally converges. All right. So if we look at this one here, same idea. Negative 1 to the n plus 1, 1 over square root of n. For sure that converges. because of the alternator on a sequence that goes to 0. But if I take that alternator away, that series would have diverged. So the only reason this converges is because of that alternator. So let's look at 3 series and just kind of ask ourselves what's going on. They all have an alternator on them. Are they converging conditionally? Absolutely. Or do they still diverge? All right. So for the first one, I have -1 to the n over square root of n. We actually just did that one here. Again, it's an alternator on a sequence that goes to 0, and so we know this converges. But if we took the alternator away, if we just had 1 over square root of n, that would diverge. So the only reason this converges is because of that alternator, therefore this is conditionally convergent. Okay. This one here, we have an alternator on a factorial over exponential. Factorial beats exponential. So this sequence, the sequence is going to go to infinity. So because the sequence goes to infinity, this series diverges. Doesn't matter that an alternator, that alternator is not going to change anything with this. This is going to blow up. And over here we have an alternator on a 1 over 3 to the n. All right, so that's definitely going to converge. 1 over 3 to the n does go to 0. All right, kind of just like on your own say, okay, that for sure works, and so I know this is good. But what if I had just took the alternator off and had 1 over 3 to the n? Well, that converges, right? It's a geometric series, r value 1/3, and so this absolutely converges. All right. So that's how we apply that. All right, the other thing we're going to learn in this is, and we're going to start teasing out this idea, that some functions, sine, cosine, e to the x, natural log of x, can be written as an infinite series of polynomial terms. Now, today this is going to look a little weird. We're actually going to show why this works this way later. But for today, we're just kind of getting introduced to this idea. All right, so sine x is x minus x cubed over 3 factorial plus this minus this, and you do that forever and ever and ever. Same thing with cosine x. All right, you're actually going to be so familiar with this that you will have this memorized and be able to recite it when needed. Okay, now if we want to use that polynomial to approximate some values of the function, how many terms should we add together? And that's a question that we can't really answer just definitively for everything. It really depends on how accurate we want to be. All right, it's how accurate. Do we want an answer that's good through 3 decimal places, 4 decimal places, 12 decimal places? That will determine how many terms we have to add up in terms of how accurate we are. So we get something called this, the alternating series remainder. Okay? If an approximation is made using a certain number of terms of an alternating series, the difference between the actual sum and the approximation will be less than the next term. Sometimes we'll say the next neglected term. Okay. What this means is this. You're going to have an alternating series that's going, has all these infinite terms to it. S sub infinity, this is the actual answer. Okay. So if I said like sine of 1, that's the actual value for sine of 1. But the actual value of sine of 1 is 1 minus 1 cubed over 3 factorial plus 1/5 over 5 factorial minus 1. Well, it's the actual sine 1 is all of those terms added together. Well, we're not going to stay, we aren't able to add up an infinite number of terms. That's silly. So the actual answer is something that we're not going to be able to do, but we could approximate it with a certain number of terms. So this is going to be our approximation. Okay. It could be 3 terms, could be 4 terms, could be 12 terms. Depends on, again, what we want there. So the difference between the actual answer and our approximation will be less than or equal to whatever that next term was, okay? So if we added 5 terms together to get this approximation, this would be the 6th term, the next term that we chose not to add, okay? So we want to decide how accurate we want to be and then find out which term is actually less than the accuracy. So for example, if we did sine 1, let's approximate sine 1 with 4 terms, okay? So this is going to be 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. All right, you put that in your calculator, that's going to give you an answer, whatever that might be, okay? So what we're saying here is that the difference between sine 1, the actual answer, minus our approximation, whatever we got there, is going to be less than or equal to the next term. The next term we chose not to use was 1 over 9 factorial. So that's going to be the maximum error, meaning that our approximation is no more than this distance away from the sine of 1. And that gives us some confidence then about how accurate we might be. 1 over 9 factorial is a very small amount. So even just adding up the first 4 terms of this gives us an answer for sine 1 that's really, really close. And so that's where these approximating functions come in pretty handy. Right? So if we do something like this here, let's say we have this alternating series. It says approximate the sum of the series with its first 6 terms, prove that this is within that of the actual sum. So let's just kind of see what these terms are. If I put 1 in, we're going to get 1 over 1, and then if I put 2 in, we'll get negative 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial minus 1 over 7 factorial. Okay, it says approximate this sum with its first 6 terms. So obviously this whole sum is all the terms, right? It's everything. It keeps going and going and going. What we're going to do is say, no, let's just do these first 6 terms. Add them together. This is going to be our approximation. We're going to say that this is a close to this value right here, okay? So the difference between the actual sum, whatever this actually equals all the way out to infinity, the actual value minus our approximation, whatever we get when we add all of that together, is less than or equal to 1 over 7 factorial, the next term. That's our maximum error. Right? And if we can understand that kind of structure and what we're saying here, then we'll do just fine when those questions come up.